Hello there. I want to introduce you to one of my favorite topics, which is the graphs of polar functions. So there's a lot to talk about, all kinds of different graphs that we'll see. This is just to give you an introduction to what we're going to do with polar graphs. We'll follow up with what we do in class. So follow along as we talk about all the different properties and different types of polar graphs we might see. So we've got a few examples that'll lead us through what all the big polar graphs look like, and then also what kind of symmetry we typically see with polar graphs. I wanted to just show you this, first of all. Right here, what we can see is I've got the graph of r is equal to 1 plus 4 cosine of k times theta. All right, and k is going to be some sort of a constant that's going to change. And as k changes, you'll notice that you get all kinds of different graphs. It's fascinating. One little change in this coefficient on the inside of the cosine graph actually changes all the different parts of this graph. So we see that, for example, at k is equal to 2, you get this interesting graph, which looks like kind of a four-leaf clover of sorts. Not really. But then right here, we get at k is equal to 1, we get a completely different graph. It's like a little loop in it, what we're going to call limacon down the road. All right, and as we go along, we get all kinds of different graphs with different levels of petals and all that sort of stuff. So let's see what we can do to fix that we might be able to produce. Example number 1, graph the following equation, r is equal to 4 cosine of theta. So the simplest way to actually graph a polar graph without having to memorize what all of them look like is just to make a table of values. So what I did right here is to make a table of values of some common angles to find our corresponding r values. And when we did our first part of the polar graphing, right, the whole idea is that we plot things with r comma theta. So if I have a theta right here, I can figure out what r corresponds to it. Remember also that if we get a negative r, we're going to go in the opposite direction of the angle that we actually have. So we have this table of values right here. And you notice that we've got a bunch of negative values right here in the middle. And we've got a couple of values where r is equal to 0. Remember, that means that we're going to be back at the pole, so or like the origin in our old terminology. So once we take those points, all right, we're going to start graphing them. So for example, we see 2 comma pi over 3, which goes right here, 2 units out at pi over 3. We have 3.46 comma pi over 6. But we also have 0 comma pi over 2, all right, which means that at this angle pi over 2, there's no radius. So we're back right here at the pole. And you notice that we also have a similar point at 0 comma 3 pi over 2. The other thing to notice is that we actually have some negative r values. So for example, negative 2 comma 2 pi over 3, that's the first one that we noticed on the table. Well, 2 pi over 3 is all the way out here. When we made r negative, though, it meant we graph this in the opposite direction. And so what you notice is there's a lot of overlap of points, because sometimes, like at 3.46 comma pi over 6, we get the same point at negative 3.46 comma 7 pi over 6, because at that 7 pi over 6, we actually graph this backwards. And so we get this graph that looks like a circle, and in fact it is. R equals 4 cosine theta is a circle that's along the x-axis with a diameter of 4, because the most we're going to be out is r equal to 4. And of course, we're going to be back at our pole at certain points as well. So this graph, 4 cosine theta, actually produces a circle with diameter of 4, a radius of 2, and it is oriented all on the x-axis. Now, as we go along, so we graphed all those order points, connected them with that smooth curve, right? There's going to be tricks for us to actually help us figure out what sort of polar graph we have. And we're going to have 3 different types of symmetry, very similar to the types of symmetry that we saw with even and odd symmetry back in the day. So our types of symmetry are with respect to the polar axis. Remember, the polar axis is the what we used to call the x-axis. It's where our polar graphs start. So an example of that would be r is equal to 1 plus 3 cosine theta. And the idea is very similar to our symmetry with respect to x. So same equation if we replace theta with negative theta. All right, so here r equals 1 plus 3 cosine theta. When I plug in negative theta, remember cosine's an even function, so we get the same thing back, and we get that symmetry. We also have symmetry with respect to the pole. That's r squared is equal to 4 sine of 2 theta. If we replace r with negative r, we're going to get the same equation. So here, notice if I plug in negative r, and for r, I'm just going to square it, and I'm going to get the exact same equation. So here, the symmetry is with respect to the pole. It's kind of like origin symmetry from before. We also can have symmetry with respect to pi over 2. All right, pi over 2 is the angle that forms the y-axis from before. So we get the same equation if we replace theta with pi minus theta. All right, and so in other words, we get the same equation across pi over 2. All right, and if we remember, pi minus theta actually produces what's called a reference angle, and so we should get the same y value if we replace there, and that's what caused our symmetry. So as an example, use symmetry to graph r is equal to 1 plus 3 cosine theta. So to check our symmetry, we check three things. We're going to replace r with negative r. That was the first type of symmetry that we saw. And when I replace r with negative r, you notice I get a completely different equation. So we have no symmetry, all right, with respect to the polar axis. That was the first type of symmetry that we see right here. Or I'm sorry, with respect to the pole. We can also replace theta with negative theta. And when I do that, I get r is equal to 1 plus 3 cosine of negative theta. Cosine is an even function, so we get the same thing back, 1 plus 3 cosine theta. So this type of symmetry works. So that's what I meant to say before. We have symmetry with respect to the polar axis, right, across what used to be the x-axis. And finally, we can replace theta with pi minus theta. So when I plug in pi minus theta in place of theta, we can use our trig formulas to break this up. Remember, cosine likes to keep cosine together and separate sine. So we have cosine of pi times cosine of theta plus 3 sine pi sine of theta. So remember, cosine not only likes to keep the cosines and sines together, but also likes to separate them with the opposite sign. So the whole point of this is because cosine of pi is equal to -1, and sine of pi is 0, we get 1 minus 3 cosine theta when we simplify, and so we do not have symmetry with respect to pi over 2. So the only type of symmetry we actually get is the symmetry that we get across the polar axis. So what does that do? How is that represented here? So notice that the points that are above this, what was formerly called the x-axis, are now reflected across that axis, and that's the only symmetry we see. No symmetry across the pole, like points here don't go over here, and then no symmetry across the pi over 2 axis, so we don't see points going over here to here. So if we have polar axis symmetry, all we needed to know was the upper half angles because we would be able to reproduce them down below. So only 0 to pi is what matters because all the values from pi to 2 pi are going to be the same values but reflected. All right, so use symmetry to graph r equals 3 plus sine theta. So we check our symmetry again. When we replace r with negative r, you see that we get a completely different equation, so that doesn't work. When we replace theta with negative theta, all right, sine is an odd function, so we get the complete opposite function right here. And when we replace theta with pi minus theta, remember that's pi over 2 axis symmetry, all right, we would plug in pi minus theta. And remember our trig formulas, this will split up into sine of pi times cosine theta minus cosine of pi times sine theta. And since sine of pi is 0, cosine of pi is -1, we end up with r equals 3 plus sine of theta. So this does indeed have symmetry across pi over 2. All right. So with our graph, what we see, since we already did that, we end up seeing that we have symmetry across this angle pi over 2. So a point like 3.5 comma pi over 6 is the same point as 3.5 comma 5 pi over 6. So you see that it's reflected over that axis. With pi over 2 symmetry, all we need to know is our right half angles, negative pi over 2 to pi over 2, because all we have to do is then reflect those points, as we can see right here, across pi over 2. So pi over 3 is reflected and has the same r value as a 2 pi over 3. Okay, there are lots of types of polar graphs that we'll be studying as we go forward, and we already saw one of them, and that was r is equal to 3 cosine of theta. That's going to produce a circle with a diameter of 3 that goes along the x-axis. So anything that's r equals a cosine theta with a constant a in front is going to produce a circle that's along our x-axis, or our polar axis, I should say. When we see r is equal to a sine of theta, here's an example right here, like r is equal to -2 sine of theta, we end up seeing a circle that's oriented along the line pi over 2. All right, so in this case, we get the same circle with diameter of 2. So whatever's out front, that coefficient is going to tell us what the diameter of the circle is. The -2, by the way, tells us which direction we're going to graph it. I'll show you that in class, but it's hard to kind of get through a video. If, however, we see something where we're adding some sort of a plus b cosine theta, so we have a coefficient in front of the cosine, but we also add a constant to it, we end up with what looks kind of like a circle, but it ends up with what's called an inner loop. So this is a limacon with an inner loop. So notice in this case that the 1 plus 4 cosine theta, the 4 number is bigger than this constant 1. So what I did was I graphed y is equal to 1 plus 4 sine of x over here. And the problem that we get is we get negative r values, all right? And then we get negative r values because this graph dips below the x-axis. Whenever we get a negative r value, that means we graph backwards. So the inner loop is actually this trying to be a circle, but it actually graphs everything in between this point right here, somewhere in between pi and 7 pi over 6, and then this point right over here, almost 2 pi. It graphs all of that backwards. So whenever you have a larger number in front of the sine or in front of the cosine, all right, you're going to end up graphing it backwards. And as we'll see in class, the cosine means that we'll graph on the x-axis, sine means we'll graph on the y-axis. So this example, sine of theta, means that we have it graphing going upwards. We also could have what's called a cardioid. So that's if a and b are equal to each other, we get what's called a cardioid. So like r equals 2 plus 2 cosine theta. And the reason for that is you see it looks kind of like a heart, cardioid shape. And the smallest value that we end up getting with r, as we can see from our example graph over here, is r is equal to 0. So that's 2 plus 2 cosine x. All right, so the closest we get to forming a little loop is when we get to r is equal to 0. So it kind of like pinches right here and then continues to graph positive r values. So we get what's called a cardioid in those situations. We get a dimpled limacon if this constant value is not quite big enough. So we also have an a plus b cosine theta or an a plus b sine theta. All right, and you notice this 1.5 plus sine theta is a constant that's pretty high. And what happens is it forms a little dimple. It's trying to get back to the axis, but doesn't quite get there. On the other hand, if we get something like 4 plus cosine theta, where your constant is really much bigger than what's in front of the cosine, then you get what's called a convex limacon, and you don't see any dimple here. The difference has to be with whether or not our constant is less than twice b. So in this case, 1.5 is less than twice 1, but 4 is not less than twice 1 here. So we're going to get no little dimple here on the right one. So just follow along. These are lots of different graphs that we'll see. We also have what's called a polar rose. This is a nice graph right here. All right, an example is r is equal to 3 sine of 5 theta. So if the coefficient's on the inside of the sine function, all right, we get this polar rose right here. So this happens with cosine or with sine, and we get n petals if n is odd. I'll demonstrate why that is in class. And we get double the number of petals if n is even. So here's a graph of 3 cosine of 4 theta. All right, and n is even in this case, so we don't get 4 petals, but we actually get 8 petals. We also have what's called a lemniscate. So this is like r squared is equal to 4 cosine of 2 theta. This is a nice little graph, looks like an infinity sign. All right, so anything that's r squared is equal to a squared cosine 2 theta, or r squared is equal to a squared sine of 2 theta. We get these nice graphs right here. Or we can get the spiral of Archimedes. So that would be something like r is equal to 3 theta plus 2. All right, so just follow along for now. I was going to lead us through a couple of examples with this, but I think that's good. We're going to talk about these in class as we go along. So in summary, basically the idea is that we want to plot points to get the sense of the polar graph. Polar graphs can have 3 different kinds of symmetry: the polar axis, theta is equal to pi over 2, and the pole. And that's it for trig graphs. We'll do plenty of practice as we get along in class. See you then.